And we'll go to current slide.
A couple of things I think I've mentioned before. This company called STEM Jobs has this new tool to connect classrooms to careers. It's called STEM Type Navigator. STEM, of course, science, technology, engineering, and math. Supposedly helps students find the type of jobs that their interest in things are. Now, none of you are lost students, are you? You're all transient? Yeah. Okay. So, last time, goodness, I take it we finished 3.2, or did we? No.
Page 115, example 4.
Okay. I put my paper in the wrong place. Yeah, I have the mark in the right place. I put my paper in the wrong place. So we're starting example 4, right? Yeah. Okay. So, any questions on anything we've done so far? All right, let's pick up and go from here. Now, here is a matrix. Let me get my pen activated. Okay. Here is a matrix A. Oh, this is what I wanted to say. I think I've said it probably several times, but I'm going to try to say it every day for the rest of the term. Research papers. 1 out of this class, out of 7. Not a good percentage. Please get those done so you can get them in. All of you have turned in the first test. One person hasn't. As soon as I get it from that person, I'll return those first tests to you. One person has turned in test 2, and I'm hoping the rest of you will be finishing those fairly soon, because it's not going to be too long before we get to test 3. Okay? This is a pretty short chapter. All right, so let's move on to example 4. Here is matrix A. 1, 4, 1, 2, negative 1, 0, and 0, 18, 4. Now, here we're trying to improve this matrix a bit so that we can determine its determinant. That's what we're going to be looking for. Now, there's a couple ways you can do the determinant, of course. First off, you could pick a row with a lot of zeros, or a column with a lot of zeros. My favorite here would be the first column. Okay? Has 1 0 in it. These are pretty small numbers. You could do that determinant fairly easily. Similarly, you could use a second row. That would work okay. About the same level of values. Or the third column would work okay. The third row would work. It's got sort of big numbers in it. But looking at that, we could reduce this a little bit by factoring out a 2 from that third column. Now, third row. Is that really going to help us a lot? I don't think so. Okay? So what might we do to simplify this a little bit more? Well, like I said, let's look at that first column. If we could get a 2, or that 2 to become a 0, that's going to make finding the determinant really easy, wouldn't it? Okay? And we could do, remember we got 3 elementary row operations. Exchanging 2 rows negates the sign of the determinant. Multiplying or dividing, like if we're going to divide by 2, that third row, that would take half of the determinant, divide the determinant by 2. I don't want to do that. But multiplying one row by a constant and adding to another row, that doesn't change the determinant at all. So let's do that, since Audrey's here. And we'll go from there. Okay? So, let's do row 2 minus 2 row 1. Okay? What does that give us? The new matrix A, or modified A, or whatever you want to call it, would be what? First row stays the same because that's the one we're using, 1, 4, 1. New second row. Zero. Negative 9. Negative 2. Okay? And we'll leave the last row the same, 0, 18, 4. Now remember, that elementary row operation does not change the determinant at all. Okay? So now it's a pretty easy thing to get the determinant of this matrix. Do the first column, and of course you're going to use the 1 there. That'll wipe out the first row. What is the sign of that 1? The position 1. That's a positive. It starts at upper left with positive. Okay? So that's going to be a 1 times, and then what's this determinant? Yes, it's negative 36 minus a minus plus 36. That's equal to 0. Whoa! That means can't use this one for certain things. The determinant is 0. Okay? Now, I want to point something out to you. Remember back when we were doing 2 by 2 matrices, all so easy? You can look at a 2 by 2 matrix and say, that was one row or one column is a multiple of another, its determinant will be 0. Every time you can do that. For 3 by 3 or anything bigger, no way you can look at that and say, oh, that's going to be 0. Okay? You can do it with a 2 by 2. You cannot do it 3 by 3 and better. There's nothing, there's no pattern there that is going to be a dead giveaway saying, oh, that determinant is 0. You actually have to do the work. And this is a pretty easy way to do it. The other way to do it, like I said, we could use one row or column that had zeros in it and go through and then do a couple of determinants. This was really easy to get that first 0 changed. Okay? Another thing we could have done is expand that, 3 by 3, recopy the first 2 columns and do the determinants that way. That's going to be a lot of calculations too. This looks like this was the easiest route to go. Okay? Now, silly me, when we got to this stage, we did our determinant, and it was easy to do. 36 minus plus 36, right? But look at that. 9 minus 2, 18, 4. Those are multiples of each other. Minus 2 times this, that one yields this one. So as soon as you see that, you could have said that determinant is going to be 0 without even doing the multiplication. I didn't notice that, but it is indeed true. There I was just talking about when you get down to a 2 by 2, you can tell by looking. I didn't look, okay, or you could have told. Now that example 4, you could have obtained the matrix with a row of all zeros by performing another elementary row operation. But why? As soon as you see 2 rows that are multiples of each other, stop. Okay? Now, notice I said, say we could expand, what they call cofactor expansion. Do, just take a row or a column and find the determinant that way. Okay? They have a little blurb on page 116 that shows when you have options to do, the one we just did is usually the best option, called row reduction. Now they show that for a 3 by 3 matrix. Cofactor expansion, you have 5 additions, 9 multiplications. Okay? If we had just brute force done it. Okay? That's a total of 14 operations. The row reduction, This one was easy because we already had 1 0. But if they had all been non-zero entities, the most you would have had was 5 additions and 10 multiplications, which would have been one more step than what we did if we'd have done a brute force cofactor expansion. But what if we had a 5 by 5 matrix? Your cofactor expansion would have been 119 additions, and Lauren's back, and 205 multiplications, for a grand total of 324 operations for a general 5 by 5. If you had done row reduction, 30 and 45, adding to 75. Whoa, much easier doing row reduction. 10 by 10, don't even think about it. 3,600,000 blah 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 thousand, more than 3.5 million additions, more than 6 million multiplications. Yeah, I don't want to go there. That's doing cofactor expansion. If you had done row reduction, 285 and 339, adding up to less than 600. Okay, I think, or just slightly more than 600, as opposed to more than 9 million. Okay. Yeah, 600 I'll take any time, even though it is a little longer to do. Okay. In fact, the number of additions alone for the cofactor expansion of an n by n matrix is n factorial minus 1. So 30 factorial would have been 2.65 times 10 to the 32. Okay, I don't even want to go there. Okay. So they say even a relatively small 30 by 30 matrix would require more than 10 to the 32 operations. Okay? If a computer could do 1 trillion operations per second, it would still take more than 1 trillion years to complete the determinant of that matrix. You don't want to go there. Row reduction would only take a few seconds. So do row reduction first, especially using multiple of one row times added to another row. That doesn't change with each other. So let's go to example 5. Here's a new matrix A. Let's go on and delete this one, because why have 2 different matrices with the same name? That may be confusing. So here's matrix A. -3, 5, 2, 2, -4, 1, 2, -4, -1, and -3, 0, 6. Okay. Now, remember we can do either row or column reductions. We're not solving the matrix, we're not coming up with an identity matrix, we're not doing any of that other stuff. We're just trying to find the determinant. Okay? Finding the determinant of that matrix. What might be the procedure you would follow? And remember, the most efficient way is row reduction. Anything look pretty obvious to be an easy row reduction for you here? Third row, I like it because it has a 0 in it. And what do you notice about that? If you do 2 times this column and add it to that column, you're eliminating 6. Remember, you can do column reduction when you're doing determinants. Don't do it when you're trying to solve a system of equations. That doesn't work. But for a determinant, it's perfectly fine. 2 times this added to that is going to like that, make that 6 become 0, right? Let's do it. Okay? So we'll do row 3 minus 2, column 3 minus, let me fix that. Okay, column 3 minus 2 times column 1. Okay? And that's not going to change your determinant at all. So write down the first column, -3, 2, -3. Write down the second column, 5, -4, 0. What's your new third column? New third column. -4, is that what you said? Okay, because it's a 2. Isn't that a +6? Oh, wait. Ha! I'm below, sorry. That is a plus. See, column 3 plus 2, column 1. Sorry. So you're right. It should be a plus there. 2 minus 6 is -4. Got it. Good deal. Next. -1 plus 4 is 3 and 0. That's what I like to see. Get rid of that. Okay? Now, at this point, in fact, the very first step, you could have factored out a 3, but why? I mean, you're going to have to multiply it back later, so let's just keep the 3. Okay? I'm going to reduce along this row. I mean, that row, and of course that'll be that column. What's the sign of my position for the -3? That's a positive, but it's still a -3, so this will be -3 times, and then you do your determinant. What does that give you? Second? Okay. This is a 15 minus a 16. Yeah. And what does that be? -1. And what's -3 times -1? 3. There's your determinant. Okay? Now let's see if they did it the same way we did. Yep, they did, I think. They threw in the extra silly thing about the -1 raised to the I plus j power. But if you forgive them that, it's not too bad to do. Okay? So it's 3. Got it. Any questions? 3 by 3s are pretty easy, aren't they? That was leading into something you should have figured out. Let's now find the determinant of a 5 by 5. Doesn't that sound like fun? Here's your new A. Big old hunker here. 2, 0, 1, 3, -2. I'm not liking the look of this at all. -2, 1, 3, 2, and -1. A 1, 0, -1, 2, 3. 3, -1, 2, 4, -3. And finally a 1, 1, 3, 2, 0. Okay. Now what's especially bad news here is that I have 3 zeros in that 5 by 5, 3 out of 25. That's not great odds. But what's the good news? Yes, 2 of the zeros are in the same column. So let's focus on this one. Okay? Now, I suggest we reduce these 2 to make a 0 there, and maybe these 2 to make a 0 there. Would that work? Yeah, it might work. Yeah, let's add these 2 together, get a 0 there, these 2 to get a 0 there, leave that one alone. That looks like that might work, right? It'd be pretty simple to do, and you get all zeros. You wind up with a -1, but that's okay. We can live with a -1. Can't we? Sure we can. So let's do row 2 plus row 4. Okay. And what will that give us? Going to leave row 1 alone, so that's 2, 0, 1, 3, minus 2. And what's our new row 2? New row 2. Row 2 plus row 4. 1, 0, 5, 6, negative 4. Leave the third row alone. 1, 0, negative 1, 2, 3. Okay. Leave the fourth row alone. 3, negative 1, 2, 4, negative 3. Okay. Now we'll do row 5 plus row 4. And what does that give you? What does that give you? 4, 0, 5, 6, negative 3. Okay. Now, let's go on and do what we can with what we just did, which is start with this negative 1, and we're going to wipe out that and that. But before we do that, we need to determine the sign of that position where that negative 1 is. What is that? Plus, minus, plus, minus, plus. You're absolutely right. So that's going to be a minus 1 times the determinant of what remains. And let's write that down, and that definitely is not looking good, is it? 2, 1, 3, negative 2. 1, 5, 6, negative 4. 1, negative 1, 2, 3, and 4, 5, 6, negative 3. Oh, a big boo hiss on this one, okay? Isn't it? What seems to be the easiest thing to work with? Actually, two things that look pretty easy. Three maybe. Okay? If I've done it right so far, then basically, if you did row 4 minus row 1, row 2, you get 2 zeros automatically there, don't you? So that may not be a bad way to go. The other thing I was looking at was using either one of these rows, and row reducing here, because those are all pretty small numbers. Or that row reduction would be pretty easy. That wouldn't be bad. This would be relatively simple. You could add these two rows together, subtract those. We already were talking about that. So, which way do you want to go? There's several ways to get there, folks. Second? Subtract row 2 from row 4. Okay. I like that too. So let's do it. Okay? Now don't forget your minus 1. That's the easy thing to do. Minus 1 times, I don't know whether to leave it in determinant form or leave it in matrix form. It really doesn't matter, but let's do that first. So row 4 minus row 2. So let's write that one down first. And what does that give us? What does that give us? Row 4 minus row 2. 3, 0, 0. Second. Okay. A negative 3 minus a minus, which is plus 4. Second. Yeah, 1. All right. Good. Okay. Now, while we're at it, I'm not sure this is going to be very helpful, but I mean, we could do it. We could add row 1 and row 3. Again, it may not be helpful, but it sure doesn't hurt anything, I don't think. You want to do that while we're doing it? What you think? Adding row 1 and 3? It looks like the simplest thing to do yet. What you think? Do it? Okay. I'm not sure it's a good move, but we'll do it. Row 1 plus row 3. So what does that become? 3, 0, 5, and 1. Okay. Now, since we're arbitrarily doing some things, why don't we keep row 3, 1, minus 1, 2, 3, and do row 2 plus 5, row 3. Is that okay? Okay, let's do that one. And what do you get?
6.
Say again?
6.
6. Row 2, yeah, right. 0.
16.
Second. 16? Is that what you said? I can't hear. Is that what you said? Is that okay? Good. I can't hear. Okay. And
1.
okay. Yeah, negative 4 plus 15 is 11. I'm not liking the look of that much at all, but at least we got down to a column of zeros. Well, not quite a column of zeros, all but 1. Okay, now before we do anything else, now first, don't forget your minus 1. Okay? Now, we're going to use this column here. Okay? And so the first thing I want to know is the sign of this position. What is it? Plus, minus, plus, minus. So minus and minus makes it a plus. So that's going to be times 1. So I'm just going to leave it off because multiply by 1 doesn't change anything. Times 3, 5, 1, 6, 16, 11, and 3, 0, 1. Now, just to continue our process here, not that we have to, we could expand this by the 3 by 3 method. It's not bad, but it's going to be a little tedious. But it looks like the easiest thing to me to do would be this minus 3 times 11. We do our column too, but back and forth, columns, rows, it doesn't matter. So how about column 1 minus 3 times column 3? Does that work for us? Yay or nay? Yeah, that would do. And then I think we're down to something fairly close. So let's do column 1 minus 3 times column 3. Okay? That's going to be a minus 1, here, hauling that around. Okay? And we're going to leave column 3 alone, which is 1, 11, 1. Leave column 2 alone, 5, 16, 0. What's our new column 1? Say again? Anyone do it? New column 1. Anybody? 0. Ooh, bonus. Yeah. Ooh, that's going to be nasty, isn't it? That's going to be a 6 minus 33, which is negative 27. Is that right? I think it's a minus 27. I'm beginning to hate my choice here, okay? But then the third one I like. 0. All right. At this point, we're going to stop our row reduction and go with the last thing. So, obviously the one, you could go with either one or two, this one or that one. Let's go with this one, okay? I don't think we can avoid the 27 at all, but we can do it. Let's go with this one. What's the sign of that position? Positive, so it's positive 1, so we don't have to worry with that. So we still got the good old minus 1 we've been hauling around all day long, okay? Times, and then you wipe out this column and that row, and you have 0 minus a minus, which is plus 5 times 27 is 35, 135, which is a negative 135. I sure hope that's the answer. If it's not, oh, goodness gracious, it is. That would be very disappointing, wouldn't it? Okay. No way to avoid a big number. I mean, the determinant is the determinant, okay? So you're going to run into some of them somewhere. We just chose this way. Now, I almost bet you the book didn't, or did they? Okay. They wrote the first one again, which was a tremendous waste of time. Okay. And then they built on row 2, not row 3. Okay. They did that one. Okay. That got them down to something they could then build on row 4, eliminate things. So that gave them a 3 by 3, and then they eliminated again. They did it very differently from what we did, but it still worked. Now, frankly, their last step I see. Yeah, okay. They happen to luck into adding 2 rows together and eliminate both of them at once. So yeah, that worked really nicely for them. But then once they did it, they still had to multiply numbers to get minus 135. I may have not have been the best choice, but they were reasonable choices, right? That finishes 3.2. By the way, I say this just about every time. Sometimes I may forget. I assign odd number problems. Why? 2 reasons. First, odd number answers are in the back of the book. So you can do the problem, check your answers. If you get it right, move on. If you don't get it right and can't figure out how you missed it, you can go to calcchat.com for worked out solutions to the odd number exercises. So do any of the odds 1 through 19. Then do either 21 or 23, or both if you choose. Any of the odds 25 to 35. There's a true-false 37 that should be at calcchat.com and in the back of the book. 3 parts. Then do either 39 or 41, or both. And then if you want to do a proof, you can do 43. That's not bad at all. Determinant of 45 is not bad. There's a guided proof, 47, only if you want to. That's up to you. Any questions? Okay, that finishes 3-2. Let's move on to 3-3. Ready? Okay, now I forgot to bring my watch up here. I went down to my office and forgot to bring it up. So y'all keep me attuned of how time is going. Because I only got 10 minutes between this class and my next class. I need to eat me a little something there. So please let me know before 11:50 gets here. I know we still got lots of time, but while we're here at a break point. All right, properties of determinants. In this section, you will learn there's 3 things to objectives here. Find the determinant of a matrix product, blah, blah, blah. Find the determinant of inverse matrix, okay, and recognize what you got there. And find the determinant of a transpose of a matrix and see what you got there. So, let's start with matrix products and scalar multiples. In this section, you'll learn several important properties of determinants. You will begin by considering the determinant of the product of 2 matrices. Okay, let me get my pen untangled here. Okay. Here we have matrix A. 1, -2, 2. It's an ugly 2, but it's okay. 0, 3, 2. And 1, 0, 1. Okay? Here's matrix B. 2, 0, 1. 0, -1, -2. And 3, 1, -2. Okay. Oh my goodness. I think I told you before, last Friday I had a treatment. And so this week has been just fatigue all week long. As the week is worn down, I'm getting tighter and tighter. So if I'm yawning too much or stretching too much, I just am running out of steam. Sorry. Now, the first thing they want us to do is find the determinant of A. Now, what would you suggest as a good first step? Row 1 from row 3? Okay, I like that idea big time. So row 3 minus row 1. Okay? And which one are we wanting to change? Leave row 3 alone and change row 1, or leave row 1 alone and change row 3? Which way are we going with that? Second?
Would it be better to leave row 1 as it is?
Leave row 1 the way it is? It's okay. It's just that you got a 0 in row 3, so I'd just about as soon do that. So if you don't mind, and I think it's a kind of a moot point, but I would kind of like to do row 1 minus row 3. Is that okay? Okay, and let's do that. The new row 1 then will be what? 0, negative 2, 1. Okay? Row 2 stays the same, 0, 3, 2, and row 3 stays the same, 1, 0, 1. Okay? It really didn't matter, I don't think, at all. So let's do our, well, that should be matrix, determinant form. What will that become? Obviously, I want to use column 1 and wipe out row 3. What is the sign of the position of that 1? Positive. So that's just going to be 1. So I'm not even going to write it down. And what do we have next? Second? Negative 7. Negative 4 minus 3 is negative 7. Good job. All right. Sorry, I also have conjunctivitis in my left eye, and it's driving me crazy too. I'm just falling apart. All right, we want to do, yuck. We want to do the determinant of B as well. Okay. Now, what might you choose to do before we start working on that? Anything? You tell me. Row 2 plus row 3?
Yeah.
Plus, okay. Yeah, I like row 2 plus row 3 also. And I think I want to leave row 2 alone and do this. So I'll go row 3 plus row 2. Okay? So I'm going to leave the top row alone, 2, 0, 1. I do that again. Okay. Now, I'm going to leave the second row alone. Yeah. Yeah, I guess I will. I don't like the minuses in there, but I'll do it. Okay? And what's your new row 3? 3, 0, negative 4. Okay. Now I'm going to expand using column 2 and, of course, row 2. What is the sign of the position of that negative 1? Positive, but it's a minus 1, so that's going to be a minus 1. And then I'm not going to write down that determinant again. We'll just do it. Okay. And that will be that product. What's that? Negative 8. Say again. Okay, negative 8 minus 3, right? Negative 8 minus 3. Negative 11. And that product is 11. Okay. Every time I say that or hear it, you know, the Scots are known to have a really rough accent, right? And there was this video or YouTube or something they did on this Scotsman going into an elevator that didn't have any buttons. You just called out the floor you wanted to go to. And he says, 11, or however the Scots say it. And the voice comes on and say, could you please say that again? And they spend about 30 minutes he's trying to get to the floor, you know. And I'm sorry, you have to calm down, you know. It's so funny. So every time I hear 11, I think that video. All right, so there we have the determinant of these two matrices. Now, the next thing they want us to do is multiply the two matrices. So can we do that up here and do AB? Now that will be a matrix, not a determinant. What size will it be? 3 by 3. And can we do that? Oh, it's been so long, hasn't it? Okay, let's do it. AB. Two. Wait, yeah, oh yeah, okay, yeah. 2, 0, 6, that would be it. 8. Whew, I stood up too fast. All right. The 1, 2 entry would be 1, 2, so that would be, which is 4. Yuck. Okay. And then the 1, 3 entry would be row 1 by column 3. That would be 5. Okay, well, I was jumping ahead. 1 plus 4 would be 5, minus 4 would then be 1 again. Plus 4 minus 4. Add the 0. So that's just a 1. I was just doing step at a time. Okay. The 2, 1 entry would be second row, first column. Six. Okay. Goodness gracious, I'm getting dizzy. 2, 2 entry will be second row, second column. Negative 1. Okay. All right. The 2, 3 entry would be second row, third column. Negative 10. Okay. And then the 3, 1 entry will be third row, first column. 5. Okay. The 2, 2 entry was having 3, 2 entry, third row, second column. 1. And the 3, 3 entry, third row, third column. Which would be negative 1. And I'll sit down on that one. Goodness gracious. Negative 1, we said, right? All right. Next, we're going to take the determinant of that product. Okay? Sort of a messy matrix, isn't it? Not just my writing. I'm not talking about that. Okay. What do you reckon we could do to do that? Could do our 3 by 3 expansion and do it that way, or we could do some row reduction. What do you think? It's up to you. You pay your money, you take your choice. What you want to do?
Why not just go ahead and do the determinant evil?
You know, expand it and do it diagonals? You could, no problem. Want to do that? Okay. It's all right. Perfectly okay. Now what I'm going to do, because it's already a little messy, I'm going to try to take out, without losing anything, these lines that are just getting in the way. And I'm going to take out that last one too.
Well, I'm going to do it like you want to do it. I was just going to do it.
It doesn't matter to me. I'm serious. You need to know how to do all the things, so it doesn't matter. Anyone want to do it other than what it was? What you're suggesting, expanding that? What's that? Which?
You can just cross.
Do the expansion? There's no problem. It's not a hard thing to do. So just copy down the first two columns again. It's 8, 4, 6, -1, and 5, 1. Okay? Now, do your down diagonals. And what does that give you? 8. Next down diagonal. Whoa! Oh, that's not a 51. That's a 5. Okay. I started to panic there. That's going to be a what? -200. Because it's a 20 times -10. Okay, -200. And then that last down diagonal is going to be a, second? +6. Got it. Now let's do our up diagonals, and that's going to be a okay, so it's going to be a 5 plus 5. Okay, and this one will be a +80. And the last up diagonal here is going to be a so +24. All right, we've got one big negative and a bunch of smaller positives. So let's add the positives together. 80 and 24 is 104, plus 8 would be 112, plus 11 is 123, right? Is that right? 123. That would be a -77, I think. Right? Okay. There's no way around a big number, okay? It was going to be a big number however we did it. That way just as good as any. Now what do we notice? At least in this problem. The product of the determinants is the determinant of the products. Isn't it? It's -7 times 11 is -77. So, could this possibly be true? That the product of the determinants is equal to the determinant of the product. It's kind of interesting, isn't it? Okay? That sure seems like what we're seeing. Okay? The determinant of a product is the product of the determinants. This is true in general, and we're going to do the next theorem. But I wanted to remind you of something. Okay? What happened if we had multiplied that in reverse order, B times A? We would have gotten a totally different product, right? But guess what? Its determinant must be the same. Huh. Even though it had been a very different product, its determinant would still have to be -77. So that's sort of interesting. Not useful, but interesting. Okay? All right. So here comes theorem 3.5. Ready for it? Can I erase? Okay. If A and B are square matrices, okay, and obviously same size, of order n, okay, both the same size of order n, then the determinant of AB is equal to the determinant of A times the determinant of B. Okay? I don't like the DETs. They're fine, but it's just more writing. I like the things that look like absolute value bars. All right, now, their proof on this one, I'm not a huge fan of. I mean, it may be the only way you can do it, but it goes back to elementary matrices and that kind of stuff. Oh my word, it's a lot of mess to do. But sure enough, you come up with a proof. I'll leave that to the student. Isn't that what math professors like to say? We'll leave, if it gets really hairy, we'll leave that to the student. Okay, so you can do that if you like. Let's do theorem 3.6 since we're on to theorems. Okay. If A is a square matrix, okay, of order n, okay, and C is a scalar, okay, then the determinant of CA is equal, anyone want to make a guess? Okay, that would be a decent guess, but remember C times A multiplies C by every element in A. Not just one time, not just one row, not just one column. Every element gets multiplied by C. So therefore you have in rows and columns, that's C raised to the nth power times the determinant of A. You talk about numbers getting big fast. That will. C to the nth times A. Okay? And that takes you back to theorem 3.3, a third property of that, and use it repeated times and you'll see that comes up. I don't want to do that one either, but you can. It's not that bad. All right. That sounds kind of rugged, doesn't it? Okay? But let's see, can we use it to our advantage? Here's example 2. Sorry. Find the determinant of this matrix. A is equal to 10, negative 20, 40, 30, 0, 50, negative 20, negative 30, 10. Says find the determinant of that. Oh my goodness. Row reduction here would be kind of brutal, wouldn't it? Or column reduction, either one. I'd want to deal either with this one or that one. Neither one of them looks all that friendly. So that would be miserable. Or not pleasant. Whatever. But can't we see that this is just 10 times something is going to give you this matrix, right? Isn't this 10 times the matrix? What would that be? 1, negative 2, 4, 30. Oh, 3. Goodness gracious. Brain's not working. 3, 0, 5, negative 2, negative 3, 1. Okay. Now, I'm at least a little more pleasantly disposed to do that one. I was just thinking like crazy, sorry. Can't rub them, but it makes them worse. But I want to rub them. Okay. What do you want to do with that? Up to you. You got several techniques in your pocket. Pull one out and use it. It hurts. Yeah. I think I'm going to have to go do something. Rinse my eye out or something. You mind Y'all want to work on this while I'm gone? Okay, what was your plan? How did you proceed? Or you didn't proceed? Second? Okay, that's what I was thinking of doing too. Is that all right with everybody? Okay, I'll erase this and just expand it because that's sort of okay to do on a 3x3. And since there was no obvious row reduction or column reduction that's going to be super easy, why not do that? Okay, so expand this, so that'll be a 1, -2, a 3, 0, and a -2, -3. Okay, now let's do our thing here. Okay, this is going to be a 10. That 10 is out there. Okay, I think it is. Let's try that. Times. Let's do the first column down, or first diagonal down. What does that give you? What? A 0. I like that. Okay. This next one gives us a 20. Is that what I heard? Okay, positive 20. That next one gives us a -36. Is that what I heard? Okay. Then let's do an up diagonal here. What does that give us? A 0. I'm in favor of that. And this one will give us a positive 15. It's a minus with a minus. Okay. And the last one gives us a +6. Okay. And what does that give us? Okay. Only one negative, and this will be 35 and 6 is 41. Subtract 36 from that, and I think you get a 5, don't you? I think so. Yeah. Okay. Now, the determinant of that is a 5, and our property we just had is that it's not just 10, it's 10 is what we factored out, but you have to raise that to this was a 3x3, so that would be 10 to the 3rd power. Okay, when you're taking the determinant, you multiply it by 10 cubed. So that will be 5,000. Okay, and sure enough, that's what they got in the book too. Okay, it's not just multiplied by 10, it's 10 raised to the nth power. And since we had a 3x3, the n was 3. Does that make sense? And sure enough, if we had done the determinant, if we had expanded that first one, then that would have been a 10 and minus 20, and you multiply all those numbers together, you're going to get a lot of zeros. And sure enough, that's what you would get. So this does make life a little bit easier. All right. Now, those two theorems together, 3.5 and 3.6, give formulas for determinants of the products of two matrices, and the scalar multiple of a matrix. Those theorems do not, however, give a formula for the determinant of the sum of two matrices. Okay? And let's just see if there's anything we can harness from that. Let's go to simple things like 2x2s. Here's matrix A. A 6, 2, 2, 1. Matrix B. A 3, 7, 0, -1. Okay. Now, what's the determinant of A? 2x2s are so much fun, aren't they? Second?
That's 6 minus 4.
Yeah, it's 2. Okay, I just can't hear. What's the determinant of B? -3. Okay? Now let's add the two matrices, A plus B. What would be, can you add those two? Sure, okay. That is a 6. I realize that doesn't look... Okay, what is that new matrix? 9, 9, 2, 0. Okay, let's do the determinant of that. A plus B. What would that be? Negative 18. All right, any way to get a negative 18 out of a 2 and negative 3? Not any way easily. Okay, I know. There is no relationship. Okay? There is no relationship between the determinant of a sum and the sum of the determinant. None. So don't even make that one up. Okay? It doesn't exist. The others are linear type things. Those are there is none for sum. Okay. Okay, how are we doing on time? Second? 11 what? 15? Okay, good. We got plenty of time. Okay, like I said, I forgot my watch. I had a pin break in my watch, so it won't stay on my wrist, and I just haven't had a chance to get that repaired. So I've been carrying it around in my pocket. I forgot to bring it up here. All right, so let's move. We talked about the matrix products and scalar multiples. Now let's go to another property of determinants, and this will be determinant of the inverse of a matrix. So let's pick a matrix. They give us one, A, and this matrix happens to be 0, 2, minus 1, 3, negative 2, 1, and 3, 2, negative 1. Okay. Here's a matrix. Here's another matrix B. 0, 2, negative 1. 3, negative 2, 1. And 3, 2, 1. Okay. Now, in general, especially 3 by 3s and higher, you can't look at them and tell whether it's got an inverse or not. However, one of these you can. Anyone want to hazard a guess? Anyone want to hazard a guess? Second? Anything? All right. Here's something to notice. Remember, we're used to thinking in terms of rows, but also look at columns. Notice here. These two columns. This is a multiple of that. Minus 2 times this gives you this. And anytime that happens, 0 taken. Zero determinant. If it's 0 determinant, that one doesn't have an inverse. Remember? Or we have said that, right? Okay. Now that one we can't guarantee it does, but at least we know this one doesn't. Okay? Again, there's no way to guarantee that one does, but we know this one doesn't because its determinant is 0. And if the determinant is 0, it doesn't have an inverse. Okay. So, let's do theorem 1.7. A square matrix A, doesn't give you what dimension it is invertible. That means it does have an inverse. Also, what's another word for being invertible? non-singular, okay? They love to throw that in there. Okay, non-singular is invertible. If and only if, there's a simple symbol for it. Another is IFF. Both of those mean if and only if. Determinant, why do I write it this way? The book did, but determinant of A is not equal to 0, okay? If you have a square matrix and its determinant is anything other than 0, you can invert it. It is invertible. It does have an inverse. But if its determinant is 0, it does not. The if and only if says, doesn't just go one way, it goes both ways. No way it will have an inverse. Okay. Now, there is a little discovery here on the side. That we're going to use in a little while. So let's go on and do them now, I guess. Okay. Here's a matrix A. 6, 4, 1. 0, 2, 3. 1, 1, 2. Okay? It says find A inverse. Now, we're not doing determinants now, we're doing A inverse. That's all, for right now. Later we're going to do something. So what would you do to find the inverse of that? It says use a graphing utility, which you could do if you got one, but it's not that awful to do. What would you do? How do you find this inverse? I'll give you a hint. I'm going to lose that. How do you find this inverse? Yes, you amend, what do they call it? Second? Augment, yeah. Augment it with the identity matrix. 1, 0, 0. Go ahead. 0, 1, 0. 0, 0, 1. Okay. Now what do we do? You want to do what?
You want the left half of it to look like the identity matrix.
Okay. What you want to do is row reduce this until it looks like that. But in so doing, that will change this to look like something else. If you get something that's not got a row of all zeros, then you have the new thing over there will be the inverse. So what do you want to do first? Do a row reduction. What's the first thing that's you want to have? A 1 in the upper left. How are we going to make that happen? There's two possibilities here. Second? Yes. For sure. The other possibility was divide by 6. I don't want to do that. Okay? So I want to just, I'm going to shorthand it and just say that. Exchange rows 1 and 3. So this will then become 1, 1, 2, 0, 0, 1, and 0, 2, 3, 0, 1, 0, and 6, 4, 1, 1, 0, 0. Done. Now, what you want to happen next? 0 where the 6 is. You already got a 0 below that 1. Fantastic. Saves us some work. But you need that 6 to become a 0, and how will you make that happen? Row 3 minus 6, row 1. Got it. Okay? Let's see if I can squeeze it in here. So we're using the first rows. We're not going to change that. 1, 1, 2, 0, 0, 1. We're not using the second row, so we leave it alone. 0, 2, 3, 0, 1, 0. And the new third row becomes 0, negative 2, negative 11. I'm not liking this much, am I? Okay. Next. Wait. Row 3 minus, isn't that just going to be a 1? Okay. And then a 0. And then a negative 6. Is that what I heard? Okay, good deal. All right, boo hiss. What's the next thing we want to happen? Anybody?
The first non-zero entry on row 2 to be a 1.
We want it to be a 1. Okay? I agree. I don't want to do the work for it, but I agree. But here's something you can do. As long as the steps are legal, you don't have to follow the same order. So since I'm going to want to have a 0 below that anyway, and I say all I have to do is add these 2 rows to make that a 0, I'm going to do that first and then go back and change that to a 1. That's okay, right? Legal in most states. So let's add row 2 plus row 3. Row 2 plus row 3. All right. Now we're leaving row 1 alone. 1, 1, 2, 0, 0, 1. We're leaving row 2 alone. Well, let's do the, what I say, row 2 plus row 3. What would that be? Help me. New row 3. 0. Negative 8. Second one? 1? Is that what you said?
Oh, that's sorry, that's 1.
Okay.
1.
Right. Got it? All right. Now we have to divide row 2 by 2. Is that all right? Row 2 divided by 2. Okay, so that becomes a 0, 1, 3 halves, 0, 1 half, and 0. Boo hiss, but it's got to be done. And the next part, well, next part is not super bad, but it's bad enough. What you want to happen next? That one above that leading 1 in row 2 needs to be a 0 too. So how are we going to do that? Row 1 minus row 2. That'll work, won't it? All right. So the middle row stays the same. 0, 1, 3 halves, 0, 1 half, 0. New top row becomes 1, 0, second, 1 half. No, you're not multiplying, just subtracting. 4 halves minus 3 halves is 1 half, right? Next. 0, negative 1 half, 1. Got it. Got it. Now the next part I really hate. That's why they said use a graphing utility or something else. What do we got to do? What do we want to happen next? That becomes 1. The only way to make that happen is Divide by negative 8. Boo hiss. The good news is a 0 stays a 0, and a 0 stays a 0, and that goes to a 1. But this becomes a negative 1/8. That becomes a negative 1/8. And that becomes a positive 3/4. Right? Okay. All right. 2 more steps. Neither of them are pleasant, but they're doable. What's the next thing we want to happen? We want half to become a 0, and the 3 has to become a 0. So the next 2 steps. How do we make that become a 0? No, that makes it 1. Okay, and that messes up this. Okay, you multiply the third row by 1/2, negative 1/2, and add it. Right? So basically, row 1 minus half of row 3. Right? Okay. Row 1 minus 1/2 of row 3. Suddenly that became B3. I don't know how that happened. I'm going to change that just to make it easier to write as minus B over 2. So here I said B again. Row 3 over 2. The old gray cells there falling apart. Okay? So that becomes, let's write down the final row. 0, 0, 1, negative 1/8, negative 1/8, 3/4. That, by the way, is the last row of your identity matrix. By the way. Okay, new row 1 will be new row 1 will be new row 1 will be help me somebody. Row 1 minus row half of row 3. 1. Okay, thank you so much. Next. 0. Next. 0. Okay, now the bad part. Okay. Not 0. It's 0 minus half of 1/8. So that would be plus 1/16. Right? Okay. Next one will be row 1, which is 8/16, negative 8/16, right? Minus or plus 1/16 is a negative 7/16. Am I doing it right? Let's see. Oh my goodness, I'm tired. Okay. Row 1. Now when I take half of this, it's going to be the 16ths. That's going to be negative 8/16. Minus and minus is plus 1/16. Make it negative 7/16. Right? And then the last one. Now when I take half of this, it's going to be 3/8. Okay? So this will be 8/8 minus 3/8 is 5/8. Okay. All right. I would say that wasn't too bad, was it? But I won't say that. Okay. Next thing we want to do. Got to get that to become a 0, right? And how are you going to do that? Row 2 minus 3/2 row 3 becomes a new row 2, right? Boo has, but we'll do it. First entry. First entry. First entry. 0, 1. Good. Next. 0. All right, that was the easy part. Okay, now the little bit tougher part, but it's still not super bad. Okay, row 2, which is 0, this isn't probably too bad, minus 3/2 of 1/8. Well, that would be plus 3/16, right? So 3/16. That wasn't too bad. 3/16. Okay. Now, a little bit worse. Okay, row 2. This again is going to turn out to be 16ths down here, so this will be 8/16, right? 1/2 is 8/16. Plus 3/16. 8/16 plus 3/16 is 8 plus 3? 11/16. There's that 11 again, okay? And then the last one, not so awful. Row 2, 0, okay? Minus 3/2 of 3/4. That's the minus 9/8, isn't it? We have 0 to begin with, so that's nothing. And then minus this times that, minus 9/8. Right? All right. Why did we do this discovery? All right, we found A inverse. I sure hope it was. Okay, so A inverse is 1/16, negative 7/16. Ooh, I can't write. 5/8, 3/16, 11/16, negative 9/8, negative 1/8, negative 1/8, 3/4, I think. All right, we found the inverse. Now we got to do the determinant of both A and the inverse of A. All right. Now, the determinant of A is not going to be so incredibly awful, I hope. But what I'm going to do is erase a bunch of stuff. Is that okay? Here's A. Okay. I'm going to erase all this. Hopefully we did it right. If we didn't do it right, you'll have to figure out where the mistakes were and correct them, okay? Because I'm not about to. Okay. I don't think this will be too bad. Okay? So what is the determinant of A? How do you want to do that? Expand, okay? Make this a 6, 4, 0, 2, and a 1, 1. Right? And let's go down. So the determinant of A is going to be, second, 24. Down again, plus 12, and down again. Yeah, okay. Then we'll do an up one here. Minus 2, and up one there. Minus 18, and an up one there. 0. Okay, got it? Okay, so 24 minus 20 would be 4 plus 12 is equal to 16. The determinant of A is 16. That wasn't so awfully bad, was it? Now, I'm not about to suggest we do A inverse the same way. Does anyone want to make a suggestion of what we do first to A inverse? Let me make a suggestion. Let's write this as 1/16 of what?
You're just getting rid of the fraction, right?
Pulling out a 16th. Yeah. Because that's the biggest denominator you have. So pull that out, and what do you have left? 1. Negative. I think it's a 7, isn't it? Making fun of my writing. I can understand that. It doesn't hurt much, okay? 10. Excellent. 3. 11. Negative 18. Negative 2. Negative 2. 12. Okay. Yeah. Okay. Now, I want to expand this one too. Yeah. I'm not looking forward to it, but we'll do it. 1, negative 7, 3, 11, and negative 2, negative 2. Okay, let's do the first one down, and that's going to be, now, since we're doing a determinant now, okay, remember that 1/16 is raised to the third power. 1 over 16 cubed. Okay, times, and what's that? 11 times 12 is 132, isn't it? 11 times 11 is 121. I think that's 132, okay? And I think it's time for a calculator here. That would be positive. Yeah, someone with a calculator, please. Say again? A little louder. 252. 252. All right, good deal. Thank you. And this will be? It's a 10, 3, negative 2. Negative 60. Okay. Now let's do your up diagonals. And what do you have here? That's 110. Double that is 220, right? It's a plus because you had 1 minus. This one becomes a 36, and this becomes, and it's a minus, and this becomes a plus. Let's see, that's a minus. It's 84 times 3. 252. Is that what you said? My brain is not working well at all right now. All right, if that is indeed a 252, get rid of those. We have two positives. That's a 352 minus a 96. 352 minus 96 will be a 256. Is that right? Okay, 256. Now, someone do 16 to the third power. What is 16 to the third power? 16 times 16. Well, what is 16 squared? Do that first.
4,096.
Okay. All right. So this will be 1 over 4,096 and multiply that by 256. So do 256 into 496. 4,096. What do you get?
0.0625.
Okay, yeah. All right, you multiplied it, right? What I said to do was divide this by that. Yeah. You got a right answer. But it's more obvious if you do it this way. Divide this by that. 4,096 divided by 256. 16. So what we have here, the determinant of this is 1 over 16. So what does it appear to be? The determinant of a matrix is 1 over that same determinant of its inverse. In other words, matrix A has an inverse matrix, A inverse. The determinant of A is 16. The determinant of A inverse is 1 over. So here's what we've got. Determinant of the inverse of A is 1 over the determinant of A. Or vice versa. That's what we got. Because the determinant of A was 16, the determinant of A inverse was 1 over 16. So at least that's what it appears. Okay? How are we doing on time? 11:46. We got 4 minutes. Okay. Now, I'm thinking example 3 is going to take us more than 4 minutes. What do you think? So let's begin with example 3 next time, and I'll wipe out this. And in fact, when you start example 3, you'll see the 2 matrices we did at the very beginning of the section at the top of page 122. Those are the same 2 matrices we're doing here. And we know the first one doesn't have an inverse because its determinant is 0, but we haven't determined the other one. So we'll do that next time. Let me give you a few homework exercises here. You can do, I think, any of the odds 1 through 5. I think you can do 9 through 11. I think you can do 13 or 15 or both. And we'll pick up the rest of those next time. Okay? Now, we've just got one more section to do, 3.4, and we're not going to do all of that, but we're going to do some of it, and we will then be ready for our next test. So, hint, hint. Get your papers in. This class, only one research paper in. One person still missing the first test. I've only got 1 second test in. So try to get working on your paper and on the second test, because I know next week, if not Tuesday, then at least by Thursday I'll be giving you your next test. Okay? Good deal. Any questions? All right. Oh, good deal. Look at this. Speaking of Athens. Okay. Thank you. All right. Does anyone need this left up here any longer? Okay. Oh, here's another. It rains, it pours. All right. And